So the field of quantum information is basically about studying quantum mechanics in a way that kind of focuses on the informational aspects of quantum states, and in particular thinking of quantum states and quantum information as a new kind of information. So, so there's a kind of a bunch of different. It's a field, as the field is kind of exploratory. There's not like a single big question that we're trying to answer, but there's a bunch of kind of major themes that recur in research in the field of quantum information. And so, of course, the first one is building a quantum computer. So I'll talk a lot more about what a quantum computer is and what it can do. But the basic idea is that people have observed that, that if you were able to build a quantum computer with where the individual components are quantum objects like single atoms or small superconducting circuits, then that computer could have more capabilities in a bunch of ways than a classical computer could. And so we're going to talk a bunch about that over the course of the class. And building quantum computers is starting to become a real-world thing, in that there's a number of big companies that have invested a lot of money in building quantum computers. There's also a lot of government funding, of course. And there's even a bunch of startups nowadays, some of which are trying to build quantum computers, and other which are writing software or doing other aspects of quantum information. So building a quantum computer is a pretty challenging task for reasons that I'll discuss a bit later on. Partly because it's a matter of dealing with very small objects that have to behave quantum mechanically, and partly because quantum states just happen to be more delicate than classical information. And those are both things that we'll see how they involve. So it's a task that involves both experimental work, of course, but also theoretical work to think of designs and to kind of improve the way of dealing with errors and things like that. So this is one kind of major theme of research, is things that will help us build a quantum computer. And then another theme is, well, suppose we had a quantum computer, what could it do? So one of the major things that you want to do with a quantum computer is to run a quantum algorithm that can solve some sort of computational problem potentially much faster than a regular classical computer could. But there's also other kinds of quantum protocols, like quantum cryptography. And those also offer some opportunities to do things that either you could not do efficiently on a classical computer, or you could not, in some cases, could not do it all. And so at the moment, this is kind of almost completely a theoretical endeavor of saying, well, if we had a big quantum computer, could we do this? Could we do that? But it's kind of approaching the stage where people can start to do experimental work, actually, on this, where you can say, well, I have some potential quantum algorithm. I mean, it is a quantum algorithm. I want to run it on a quantum computer, but I don't know how to analyze it theoretically. It's too hard to analyze theoretically. And we're kind of almost at the stage where you can try it on a real quantum computer and see what happens. But we're not quite there yet. The current quantum computers are kind of just at the edge of what you can efficiently simulate. Well, efficiently is not maybe a good word. That you can reasonably simulate on today's big classical computers. And another aspect of this is we're not just interested in what you could do with a quantum computer or things that, communications, quantum communications, not just the technological aspects of it, but more generally, when we think of quantum states as information, what properties do they have? And in particular, how do they differ? How do those properties differ from classical information? And we'll find that there are many ways in which quantum information is similar to classical information, but there's also some key ways in which it's different. And this is kind of a very in principle and foundational aspect of the field of quantum information. We just want to understand kind of the real difference between quantum and classical. And this is a particular way of doing that. And so one advantage of doing that is that these insights and the techniques that we develop in the field of quantum information are starting to be used in a bunch of different areas of physics. And that's because a lot of areas of physics deal with quantum mechanics, right? They deal with quantum systems. Condensed matter deals with quantum systems all the time. And indeed, quantum information ideas are starting to be making a big inroad into condensed matter. People discovering new phases of matter, understanding topologically ordered materials in terms of their entanglement properties or quantum error correcting code properties, things like that. In fact, there's a whole kind of subfield sort of on the border of condensed matter and atomic physics of cold atoms, where people will do all sorts of cool things with atoms trapped in optical lattices. And this is a field that basically grew out of people thinking about how to build a quantum computer. Another thing that's happened in past 5 years or so is a growth of more and more people in high energy, in particular string theory, working on ADS-CFT and related things, thinking about quantum information aspects of those systems and how quantum information ideas can provide them some insight and help them understand better what's going on. So I'm not really going to talk about any of this stuff during this class, though feel free to ask questions if you have some specific ones. But it's starting to be a big aspect of the field of quantum information as well, and these other fields. And then the flip side of that is that actually studying quantum information can give us insight into classical information that we didn't have before. And people are using, in some cases, there's maybe two aspects of this. Some are coming up with quantum information ideas that help them prove or derive stuff about classical computer science. And the other side of it is sometimes people will come up with a quantum algorithm for something or a quantum protocol and then realize that the quantum part is not really so efficient or so necessary. And so they'll have kind of quantum-inspired classical things. OK? So yeah, so that's kind of an overview of the field of quantum information. Any questions about that so far? Yeah.
Is there any prediction about like a robust prediction, like the timescale for having like a more efficient quantum computer?
Yeah, well, it depends what you want out of your quantum computer. So robust prediction, probably not. I mean, in the next, say, 5 to 10 years, people are thinking about something that's called NISQ quantum devices. So noisy intermediate scale quantum, NISQ. And the idea would be these are quantum computers that are big enough that you really can't simulate them very well with existing classical machines, but they're not really big enough to kind of run the full range of quantum algorithms and quantum error correction that we would want to do the stuff that I'll mostly be talking about in this class. And so those are people are trying to come up with algorithms that are robust and could still work under those circumstances that can kind of give you something interesting beyond what you could do with classical computers. Beyond that, who knows exactly how long the technology will take to develop. Anything else? OK, so this is the rear. OK, so then let's get started with the technical stuff, although at least some of this will be review for those who were paying attention, hopefully, in the quantum mechanics class and those who've taken the quantum foundations class. But some of it, I'm sure, will be new today, even for those people. So the first, most basic thing is what do we talk about in the field of quantum information? And mostly what we talk about is finite dimensional Hilbert spaces. You can talk about quantum information aspects in infinite dimensions, but usually we don't. Mostly we want to talk about much smaller systems because they're simpler. And in classical computation, usually you talk about computers built out of bits, right? A bit is a 0 or 1. It has 2 values. And so the quantum version of that is going to be a 2-dimensional Hilbert space called a qubit for quantum bit. And so just as the classical bit has values 0 and 1, we like to think of those as labels for the basis elements of a qubit. And so the qubit will have basis states ket 0 and ket 1. Right? But of course, you can do any superposition of those things. That's a valid quantum state. So you're going to have states like alpha 0 plus beta 1. And of course, quantum state, really, this should be normalized. Alpha squared plus beta squared is 1. Most of the time, I'm not going to bother with that. There may be a couple of instances where it's important enough that I want to take care of it. But the normalization you can always just put in, right? It's some constant that you divide by. OK, so that's a single qubit is a 2-dimensional Hilbert space. But what happens if you have 2 qubits? Well, that's going to be the tensor product of 2 2-dimensional Hilbert spaces. So it's a 4-dimensional Hilbert space. And if we have 2 classical bits, well, they could have 4 values, right? 0, 0, 0, 1, 1, 0, 1, 1. And so again, those will be the basis states, labels for the basis states of a 2-qubit system. And in general, if we have n qubits, that's going to be a 2 to the n dimensional Hilbert space. With the basis states in the standard basis labeled by bit strings of length n. And so the most general state we can get there is sum over x alpha x x. But it's also important that we derive this Hilbert space as a tensor product of 2-dimensional Hilbert spaces. That decomposition into qubits is really important. And usually there's kind of a preferred tensor product decomposition that's given by the physics of your system. But when we're talking theoretically, we forget about the details of why it happened and just say, well, it is this tensor product. And the tensor product is important because it creates a kind of a distinction between different kinds of states. So we have some states that are tensor product states, or people will often just say product states. And so they might be something like 0 plus 1. You see I've already dropped the normalization. Tensor 0 minus 1. But then you have states in the 4-dimensional Hilbert space that are not tensor products. They're entangled states. So you get states like this EPR pair, 0, 0 plus 1, 1. OK? And this cannot be written in this form as a tensor product of 2 things. And so I guess I don't know if Aggie did it in the quantum mechanics course, but I'm sure if you've taken the quantum foundations course, you heard about how entangled states can exhibit correlations that are stronger than any tensor product state, any kind of classical correlation. OK. And so this is what's going to be the state of our computer. It's going to be some n-qubit system, n-qubit quantum computer with some arbitrary, potentially entangled state. And then the updates that we do to the system, it's not enough for a computer just to have a state. We want to change that state in order to do computations. And so a computation is going to be some unitary operator. But it's not going to be an arbitrary unitary operator. We want to break it up into simple steps. Right? It's not enough to say, oh, we're just going to do some big unitary that gives us the answer to this question. That's not a reasonable type of computation because it's kind of cheating, right? You couldn't actually build that because you don't know how to make that giant unitary. Instead, you want to build it up out of a kind of small set of standard operations that only act on a small number of qubits at a time. And those are called quantum gates. So quantum gate is, I mean, potentially it could be a many qubit gate, but mostly people talk about 1 or 2 qubit gates, or sometimes 3 qubit gate. So 1 qubit gate acts on a single qubit in this tensor product. And it's just going to be some unitary that is then the tensor product of identity on n minus 1 qubits with something non-trivial on 1 qubit. And similarly, a 2 qubit gate acts on 2 qubits non-trivially. Okay, and a 3 qubit gate acts on 3 qubits, and so on. Okay? Yeah?
I don't understand the notation. What do you mean by 0, 0 there?
Right. So this is a state of 2 qubits. So it's a 4-dimensional Hilbert space. And remember, I want to label the basis states by classical bit strings of the same number of bits, so 2 bits. And so there's 4 2-bit bit strings, 0, 0, 0, 1, 1, 0, 1, 1. So that's the label.
Oh, okay.
But it's also, there's some kind of implicit tensor product here in this state 0, 0. So I could equally well write this as 0 tensor 0 plus 1 tensor 1. Okay, so these are the same thing. This is just different notation for the same thing. But it's kind of worthwhile understanding that this label 0, 0 is the tensor product basis that you can write this way, but it's just kind of 2 different ways of thinking of the same thing. Okay? Are there other questions? Okay, so the thing is that these quantum gates, I said they're going to be unitary operations. Okay, that's not really completely essential, but it's certainly the main thing that you'll see. The thing about unitary operations is that so we're taking the state psi to u psi. And that means that unitary operations, you have u dagger is equal to u inverse, right? So if you take u dagger applied to u psi, you'll get back psi. And that would also be an allowed quantum gate. It might or might not be in this set of things that you can do easily, but you should be able to do it, right? It's a unitary operation. And in particular, this means that any gate we do is going to have to be reversible, right? We go forward from psi to u psi, but then we can go back to psi if we wanted to. And that's already a big difference from how people normally think about classical computation. So what we have to do is before we really get started on quantum computing, we have to develop the theory of reversible classical computing. which is luckily not too complicated. I mean, I'm not going to go into all the details about it. But the basic idea is quite simple. So first of all, so classical computing, you can also think of it as a series of gates, which now are going to be simple classical maps between bit strings. Again, you want to think of them as acting on 1 or 2 qubits, or sorry, 1 or 2 bits or 3 bits. And some of those gates are already reversible. So here's an easy example. The NOT gate. So what does a NOT gate do? Well, we can write its behavior in terms of a truth table. So we're going to have the input bit and the output bit, and it's a single bit operation. So you're supposed to the name comes from thinking of the 0 and the 1 as true and false. I guess probably 1 is true and 0 is false. Okay, so that's another kind of way of rewriting the classical bit. And not will take true and make it false, and false and make it true, right? So if it's not true, then it's false. And if it's not false, then it's true. So 0 should go to 1, and 1 should go to 0. And clearly this is reversible, right? Because if you just do not again, you get back to where you started. So another example of reversible gate is the XOR gate. So XOR is a 2-bit gate. So we're going to need a little more space for our truth table. And so there's now 4 possible input states: 0, 0, 0, 1, 1, 0, 1, 1. So the XOR, so it's a little more subtle how the XOR is reversible. So the XOR, normally what you're going to do is you're going to take these 2 bits and kind of add them mod 2. So this is the exclusive OR. It's like this or this, if you think of them as true or false, but not both of them. So what that means is that 0, 0, you add the mod 2, 0 plus 0 is 0. And here, let me make a little space here. So this is, we think of this as bit A, and this is bit B, and we can write the XOR as this kind of circled plus. And 0, 1, we add those together, we get 1, 1, 0, 1. But 1, 1, that's kind of the both true case, right? So that's supposed to be 0. And 1 plus 1 is 0 mod 2. So this is A plus B. Now, if you just look at this, it's clearly not reversible. Because, well, we have only 1 output bit and we had 2 input bits. So we can't possibly have all the information that we need to go backwards. But that's kind of not really fair, right? We had 2 input bits. We might as well have 2 output bits. So we can keep around some of this information. So let's keep around A. OK, so we'll keep around A here. And I'll just copy that over. And so now we have a version of XOR that has 2 input bits and 2 output bits. And if you look at this, this is reversible. Because if you XOR, so what did this do? It took these 2 just stayed the same, and these 2 just switched places. Right? And so if we do XOR again, these 2 will switch back, and we'll get back to where we started. OK, so this is also a reversible gate. OK, so maybe at this point, it doesn't seem like this is going to be so hard. But the next example shows that it's a little more complicated. And this is another pretty standard gate, the AND gate. Again, it's a 2-bit gate. So the AND gate, if you think of it, it's the name AND comes again from thing of truth values. So if you have A and B, that's only the AND is only going to be 1 if they're both true, right? True if you know, I am giving this class and I'm man, then that's only true if both of those statements are true. You can also think of it as the product mod 2. So you multiply these things together, and you get 0, 1, mod 2. And again, that happens only if both of them are 1. Right? So what do we get here? We get 0, 0, 0, and 1. And so obviously, again, this is not reversible by itself because we have 2 input bits and 1 output bit. But what happens if we do the same thing and keep around the first input bit? So now look at this, and we'll see it's still not reversible, right? Because we have 2 0, 0 outputs. So if we get 1 0, we know it had to come from here. And if we get 1 1, we know it had to come from here. But if we get 0 0, we don't know whether the second bit was 0 or 1. OK? So this is not reversible. OK? So what are we going to do? Because obviously, if we want to build reversible classical computers, we still need to be able to do something like an AND gate. Right? Otherwise, we'd be very limited to what we can do, is only doing things like NOT and XOR. And it turns out the solution is to not make it a 2-bit gate, but to make it a 3-bit gate. So this is the Toffoli gate. And so the Toffoli gate is a 3-bit gate where we have three input bits, A, B, and C, and 3 output bits, which are going to be A, B, and C plus A times B, mod 2. So let's write out the whole truth table here. Sorry, can everybody see this, or am I getting behind?
Probably can raise the board a little.
Yeah, I can. That's true. Not too much, because then I won't be able to reach it. OK. OK, so we're going to keep around the first 2 bits unchanged. So I'm just going to copy them over. And then the last one is C plus 8B. So what does that mean? That means that I'm going to do the XOR. I'm going to calculate the product of A and B. And then I'm going to calculate the XOR with C. So if C is, well, so OK, I guess the easiest way to do it is these first 6, A times B is 0. And so C is just going to get copied over directly. So we get 0, 1, 0, 1, 0, 1. And then in these last 2, A times B is 1. And so the XOR is going to flip the 0 and the 1. It's a NOT on C in that case. So 1, 0. So what we've done here is we've just mapped these all over, and then these 2 switched. So again, this is a reversible gate. And if you do the Toffoli gate again, you get back to where you started. So I should note that in all these examples, the gates that I showed you are their own inverses. If you do them again, get back to where you started. That doesn't have to be the case. This just happens to be true of these kind of simple standard gates. Yeah?
Do gates have to map n bits to n bits?
Well, OK, so in order to be reversible, you certainly can't map n bits to fewer than n bits, right? Now, in principle, you could map n bits to more than n bits. But if you think about it, really what's happening there is you're like in this case, you're going to have some third bit that's kind of sitting around, and it started out in a standard state. And so, for instance, if you start out with the state AB0, right? So you have this third extra bit, and then you apply the Toffoli gate, then you get AB, and then here, let me put commas to make it clear, A times B. And so this is a gate that's mapping 2 bits to 3 bits. But really what it is a special case of this Toffoli gate, where we're just kind of not really caring about what happens when the third bit starts as 1. Okay? So it's usually more helpful to think of it as mapping the same dimension to the same dimension. Well, OK, that's not exactly true. Frequently, we'll talk about it maybe in such a way that this is kind of taken for granted. But really what's going on at kind of the fundamental level is this, that it really is an end-to-end. And part of that is so that when you do the inverse, it's also an end-to-end map, and it's a complete map, right? Because otherwise, the inverse map would have to take 3 bits down to 2 bits, which would be non-reversible if you tried to extend it to the whole 3-bit state. And you want your gates to be able to act on arbitrary states because you don't know exactly what state it's going to be. Does that make sense?
Yes.
OK.
About one-to-one maps. I mean, you want it to be one-to-one. So
Well, right. So this is all. This is still classical, so it's all finite dimensional. And so in order to be reversible, they have to be one-to-one and injective. Certainly, they're always going to have to be one-to-one, even if you had some infinite set of strings. But they wouldn't have to be surjective, right? They wouldn't have to be onto if it's infinite. But for finite, it has to be both. Any other questions? Yeah. So anyway, so the point is that this Toffoli gate is a 3-bit gate. It's reversible. But it also, through this trick, implements the AND. Right? You see this here in the third, by putting the 0 in the third bit input, we got the AND computed in the output. So this is kind of the way that you make AND reversible. Is you keep around not just one input, but both inputs. Whereas with XOR, we only need to keep around one input. OK. So there are other questions about these reversible, kind of fundamental reversible gates. OK. So of course, what we want to do in classical computation is not just a single 3-bit gate. We want to do some more complicated computation. And we do that by building up these gates into what's called a circuit. Oh, yeah, so I guess I'll need this back. So a circuit diagram, and we're going to use this a lot in quantum computation, is going to use some lines that represent bits, or in the quantum case, qubits, and then some symbols that we put on the lines to represent the gates. So a common notation, at least in the quantum computing community. So first of all, this is a bit here now, or a qubit later. And time goes this direction, left to right. And then the NOT gate looks like that, kind of a plus in a circle. OK? And then the XOR gate is a 2-bit gate. And so we have a control bit that stays the same and a target bit that gets flipped, potentially. And we usually draw this like this. OK? So this circled plus can remind you of that plus there. And this small dot is the one that's controlling the other one. OK? Does this make sense so far? And then the AND we're not going to need because it's not reversible. But the Toffoli gate is a 3-bit gate. And you see it looks very similar. It's flipping this third one, but now it has 2 control bits. And so this is supposed to represent taking the AND here and then XORing it with this third bit. OK? And then we can put these pictures together to make a circuit. So an example, suppose we want to calculate something more complicated. So suppose we want to calculate, given 3 input bits, we want to calculate the product, ABC, which we could break up into smaller non-reversible gates as A and B and C. OK? So this is kind of supposed to represent our big computation. And here it is broken up into fundamental gates. First, we calculate the AND of A and B. And then we take the output of that and calculate its AND with C. So how are we going to convert this into reversible gates? Well, so we're going to need, as it turns out, 5 bits. And so the AND of A and B, we're going to remember here. So these inputs will start A, B, C. And then these ones are going to start with 0. Those are our extra bits called ancilla bits. And so we're going to implement this AND using the Toffoli gate with the trick that I said. So we're going to take one of these ancillas, and we're going to calculate the AND with it, like that. And so you see this line here is crossing the C line, but there's no dot, so it's not doing anything to the C line. It's leaving that bit alone. It's just interacting this bit, and this bit. OK? And so at this point, this bit has the value A times B. And then what we want to do is we want to take the AND of that with C. So we're going to do another Toffoli gate between C and that bit and put it on the third ancilla bit. OK? And so at this point, we've calculated the thing that we want, ABC. So we've made our big circuit out of smaller circuits. However, there's kind of a problem. It's kind of a problem, kind of not a problem, which is that we have this leftover scratch bit here, which is still in the value AB. And that's a little messy. But we can clean it up. How do we clean it up? We clean it up by uncomputing it. So we're going to take this initial gate and undo it. OK? And so at this point, we get the output 0, right? Because this had the value AB. And if we take AB plus AB, we get 0. And so then this output is ABC. And these 3 have the same as their input values, ABC. And so if you look at the whole thing, it's a reversible gate as well. Now a kind of a 4-bit reversible gate, right? We're taking ABC0 and mapping it to ABC, ABC. And of course, if we had something other than 0 here, D, we'd have ABC plus D if we did this circuit. So that's an example, again, of what I was talking about, of how we're having, in some sense, we're having 3 bits going to 4 bits, but in other, it's really the 4th bit had to be there all along. OK? Does that make sense? So, and this uncomputing part, you can do in a much more general context. So, so maybe this gives you kind of the rule of how you can take a classical non-reversible circuit and make it into a reversible circuit by, well, whenever you have a reversible gate, you just implement it, NOT or XOR, you just implement it directly. And if you have a non-reversible gate like AND, you make the reversible version by adding enough, adding really a single bit. But that creates scratch bits. And so what we're going to do in general, if you have some n-bit thing, we'll have some ancillas. And so we can do this circuit C. And then in the very general case, maybe you don't know exactly where the output bit is. So we'll add one more ancilla if necessary. And this is our output. And then C is reversible, so we can do C inverse here. OK? And then these things go back to 0, and these are the same as the input values. So they might have changed along the way here, but at this stage, this XOR doesn't do anything to this bit. So this thing here, at this point, is the output of C. So doing C and then C inverse will always get us back to the starting. So this is kind of a general thing we can do to always uncompute. It's still a bit inefficient because we could potentially need one ancilla bit and one scratch bit for each non-reversible gate we do. That could potentially be a fair amount. But there are more efficient ways of doing it, which is one of the problems on the tutorial, although it's a kind of a more advanced problem. So it's supposed to be a bit challenging. OK? So let me say that one of the reasons I'm making a big deal about this is that if you leave these scratch bits lying around and you don't erase them, in the quantum context, which is what we're really interested in, things break down. Your quantum algorithms will not work if you do that. So it's really important, actually, to be able to erase these scratch bits when you need to. OK? Any questions on this? I'm going to go back to talking about quantum gates now. So if you have questions about the classical reversible gates, now's a good time. OK? OK, so quantum gates. Do I want to? OK, so quantum gates should be unitary operations. And if it's a 1-qubit quantum gate, it should act on a single 2-dimensional Hilbert space. If it's a 2-qubit gate, it should act on a tensor product of 2 qubits to 4-dimensional Hilbert space. But other than that, we could consider kind of arbitrary unitaries. So what are some examples of the types of quantum gates we'll want to deal with? Well, one thing we'd like to do is we'd like to be able to kind of replicate classical computation with our quantum computer. And we can do that by taking these reversible classical gates and converting them into quantum gates. So how can we do that? Well, it's really quite simple. We take the things we had up there, and we put kets around them. OK? So for instance, if we take the XOR gate and put kets around them, we have the inputs AB, and the output will be A plus B. Of course, this is just saying what it does to the basis state. But if you have an arbitrary superposition, so first of all, before I do that, this in the classical case, this is most often called the XOR. In the quantum case, it's actually most often called the C0 for controlled NOT gate, but it's the same gate. And when we draw quantum circuits, we draw it the same way with this little dot and the big circle on the line. So this is just saying what happens to basis states. But we can also talk about C0 on an arbitrary 2-qubit state. And the thing is that we don't have to derive this separately. It just follows automatically from this rule because quantum mechanics is linear. And so if we know what happens to a basis, we can extend that linearly to arbitrary states. So how do we do that? Well, we keep the coefficients the same, and we just update each of these kets according to this rule. So this is going to go, well, 0, 0 goes to 0, 0 plus 0, which is 0. And 0, 1 goes to 0, 1. But then remember, 1, 0 goes to 1, 1. And 1, 1 goes to 1, 0. So this is what happens to this arbitrary 2-qubit state. OK? So this is one quantum gate. So another quantum gate is the Toffoli gate. And that's a 3-qubit quantum gate. Again, created just by putting kets around the classical thing. And you can extend that linearly to arbitrary 3-qubit states. OK? But the problem with this strategy for coming up with quantum gates is that we'll never get anything that's not a classical computation. In order to do something interesting, we have to do something that doesn't map basis states to basis states, that changes basis states in some kind of quantumly non-trivial way. So here's some examples. So this is called the Hadamard transform. So of course, the quantum gates are unitary matrices, so we can think of them as 2-by-2 matrices, or for single qubit gates. So this is a 1-qubit gate, Hadamard, and it's this matrix. Let me get the minus in the right place. And so what does it do? It takes 0 to 0 plus 1. Well, 1 over root 2 times 0 plus 1, if you put in the normalization. And 1 goes to 0 minus 1. OK? And this is kind of one of the most important quantum gates because it's something that's fundamentally quantum, right? It's not a classical gate. So it's worth noting, just as a kind of important separate fact, that if you calculate h squared, you get the identity. So h is its own inverse, which you can see. Well, I mean, I guess I didn't prove to you that it's unitary, but you can see, given that it's unitary, if you take that for granted, then obviously the adjoint is the same. But you could also find that, for instance, just by multiplying this together with itself. So another example of a quantum gate is a phase rotation. So I'm going to write this as r theta. And it has the matrix 1 e to the I theta. So this is a diagonal gate. And it's going to map 0 to 0 and 1 to e to the I theta 1. So obviously, this is something that does map basis states to basis states, but it maps them with a phase angle. So if you only had these classical gates plus the phase gate, this would not be very interesting, right? Because you'd start out in some basis state, you'd change, you do some other basis state, and you'd get some phase, but who cares, right? It's just an overall. It would just be an overall phase then. But once you combine it with the Hadamard transform, now interesting things can happen, right? Because you can do some classical computation, you can do a Hadamard, now you have a superposition. And this phase is going to act differently on the different states in the superposition. And then if you do another Hadamard, or another kind of basis changing gate, then you get some interesting interference effects. So for instance, if you do the, I I guess it's the pi over 2. Sorry, no, the pi phase gate here, which is, yeah, OK, I guess, right. I kind of prefer a different notation, but the pi phase gate here, that's the z, right, the sigma z, the Pauli, that it takes 0 to 0 and 1 to minus 1. And so what if we do take a single qubit, starts at 0. Here, let me write the. So here's how we usually write the Hadamard transform in terms of a gate. And this one could be like this in terms of our circuit notation. And so let's do this little circuit. What if we do Hadamard, R pi Hadamard, on a state that started at 0? What do we get? Well, when we do the Hadamard, we get 0 plus 1. And then the R pi, well, the 0 goes to 0, and the 1 goes to minus 1. Right? And so now instead of 0 plus 1, we have 0 minus 1. And then when we do the Hadamard again, we're flipping back, and now we have a 1, the output. OK? So you see how this phase and the Hadamard can interact in an interesting way. And of course, this is still obviously just a classical gate. We've done the NOT gate. But in more complicated situations, it can do something much more interesting. OK? So when we make quantum circuits, it's worth noting that there's, in some sense, the unitary operations are going to do most of the work. Those are the things that we think of usually as the quantum circuit. But there's other elements of the circuit that are also important in the sense that we wouldn't be able to make the thing work without them. And so one of them is state preparation. So for instance, we should be able to make some states in a standard state that we can start the computation in. And when we use ancilla states, extra qubits, like for scratch bits, we'll want to start them here as well. And the other thing is that we do all this computation. We get a quantum state at the end. But really, we'd like to convert that into some classical information so that we can learn, if we've done some algorithm, we can learn the answer. And so measurement is also important. And it's enough to have measurement in just one basis, say the standard basis. So then if we have some arbitrary superposition, alpha 0, 0 plus beta 0, 1, et cetera, if we measure, well, we should be able to measure either single qubit or both qubits. If we measure both qubits, we'll get output 0, 0 with probability alpha squared. If we measure just the first qubit, well, we'll get the output 0 with probability alpha squared plus beta squared. Right? OK. OK, so are there any questions on these quantum gates? OK, so maybe then I'll finish the lecture by kind of giving you a taste of why it's important to uncompute things. So let's see. So I can move this one down. Up. So suppose we do this circuit, this same circuit. Now we're thinking of it as a quantum circuit. And I want to try comparing the version where we erase the scratch bit with the version that we don't erase the scratch bit. And you'll see that we get different states that way. So let's take as input 0, 0, 0 plus 1, 1, 0. OK? Oops. OK, so in order to do that circuit, we're going to need to have two ancilla qubits. So let's put them on explicitly. And so if we don't erase, so if we're stopping here, and we don't erase the scratch bits, what do we have? Well, these things will be in the original state, at least for the basis states. And this will be A times B, and this will be A, B, C. So what do we get here? Well, we get 0, 0, 0. And then the ancilla bits, well, AB is 0 still, and ABC is also 0. And then for this one, we get 1, 1, 0. And then AB is 1. And but ABC is still 0. OK? And so what happens now is if you ignore this scratch bit, we have a mixed state. And hopefully you remember about pure states versus mixed states. If not, I'll review it tomorrow or the day after. OK, anyway, this is the state that we get when you trace out that fourth bit. But now let's consider the case where we erased that scratched bit. Well, now we have this is still 0, 0, 0, 0, 0. But this one, we've erased the scratch bit, so it's 0. And this output bit is also 0. OK? And so now the fourth bit is in the tensor product with the other ones. And so when we trace out, when we drop the fourth bit, fourth qubit, we get a pure state. OK? And of course, the whole point of quantum computing is you want to take advantage of interference between different classical possibilities. And that's going to be kind of the engine that drives the advantages of quantum algorithms. And so you can maybe imagine that going to a mixed state is not a good thing to do, particularly over something that's unimportant as a scratch bit. And whereas this pure state gives us the opportunity to interfere these two branches, this mixed state does not, right? We have either this or this, but not the superposition. So we're not going to be able to interfere. And so we'll revisit this next week with a concrete algorithm where you can actually see how erasing or not erasing really matters. OK? So I think that's it for today. Are there other questions? Yeah.
So when you're erasing, you're essentially just resetting the scratch bit to its original.
Well, I'm not. But the thing is, I can't just throw it away and replace it with a 0, right? Because that would be something incoherent, and that would leave us with this mixed state. So I have to do it in a coherent way, which means undoing the computation that got there. I mean, there might be other ways of undoing that, but it has to be something that's in itself a reversible operation, or a unitary operation in the quantum case. Yeah.
So is the fact that we had to consider larger gates, or gates acting on a larger number of qubits, related to purification, larger Hilbert spaces?
I don't think so. There may be some way of phrasing it so it's related. Certainly not the standard approach. It's kind of two separate things, which is just that classically irreversible things are normal, right? But quantumly we want to we need to keep extra information around in order to make that work. Yeah, I would not normally think of it as something that's related to purification. Any other questions? OK, then thanks. See you tomorrow when we'll talk about universal gate set and some simple quantum protocols.